Okay, good morning, everyone. Let's get started. Happy to see people still coming to the classroom. Let's hope it lasts for a few more weeks. Okay, all right, so let's begin chapter 1, Introduction to Electronics. Let me just talk a little bit about how it pertains to your studies in electronics and the courses that you will take and the differences between circuits and electronics. So let's bring this over here. And okay, hopefully sharing the right screen. All right, let's get started. Chapter 1, Introduction to Electronics. So far, you have taken circuit analysis courses, EE 113, 211, 212, circuits 1, 2, and 3. These are pretty much the same circuit class that I took when I was a student, decades ago. Everyone in the world who studies electrical engineering takes pretty much the same classes. And then when we move on to the third year, we take these electronics classes. So what is the difference? Well, in circuits, we look at linear elements, the foundational components of electrical engineering or any electric circuit for that matter, resistors, capacitors, and inductors, right? Linear elements, resistors, capacitors, and inductors. The reason we call them linear elements is because the relationship between the voltage and current is linear, okay? Relationship between the voltage and current is linear. VI characteristics. As voltage increases, current increases. As voltage decreases, current decreases, and vice versa. Even for a capacitor and an inductor, we have differential equations. Its capacitor current is IC dV over dt. Inductor is LDI over dt. It is still a linear relationship between the voltage and the current. For electronics, the electronic devices that we're going to look at, PN junctions, NPN junctions, NPN transistors, PNP transistors, these are all nonlinear devices. Okay, the relationship between the voltage and the current is not linear anymore. So at any given point in time, depending on the value of the voltage or the current, the the values would be very different. The voltage and the current would not necessarily increase with an increase of the other quantity. That's what it means. So semiconductor devices are nonlinear elements because the V and I relationship are not linear. The courses that you studied for electric circuits, as I stated earlier, is 113, 211, and 212. And here, I'll talk a little bit more about this on the next slide. But here you're studying 306, 307, and 308. And actually even 409. Okay. The analysis for electric circuits is pretty much or predominantly analytical versus electronic analysis where it's numerical. Now, the difference between analytical and numerical would be the analytical analysis is exact. You get the exact values by using one single equation. For instance, Ohm's law, V equals IR. If you were to apply this equation to a resistor, if you know two of the three quantities, you can easily find the third. Disregarding any temperature variations, any other pressure variations, other boundary conditions, this equation is valid for all, other than extreme temperatures, it is valid for all other conditions. Right? Ohm's law is valid between a certain temperature and pressure. But for all intents and purposes, if you're talking about room temperature or everyday use, then Ohm's law is always valid. You plug in the voltage values and the resistor values, you would obtain a current value, one single equation. So the analysis is based on one single equation. It gives you an exact value, hence analytical in that sense. For a electronic device like diode, BJTs, especially transistors, FETs, MOSFETs, it's not the case. The analysis is more numerical. There is never one single exact answer to your circuit condition or to the device condition. Okay. Depending on the certain applied voltages, depending on the boundary conditions, the values that you obtain may or may not be correct. The analysis is always approximate. In numerical analysis, what we do is we take approximate models. We create several different models for our devices, and then depending on which model fits our conditions best, we use that equation. So no one single equation will describe our device in all conditions. For every different condition, we'd have a different model. So depending on what we want, we would use that kind of model. Numerical analysis, we make an assumption. We try one model first, then we look at our solution, see if the solution makes sense. If it doesn't, we go back and perform an iterative analysis. We perhaps try the same model with different variations, or we try a different model to fit our conditions. And so numerical models are not always exact. They are approximate solutions. And that's the biggest difference between circuit analysis and electronics. Okay. Let's take a 10-second pause, think over that. Let me know if you have any questions. Any questions? Okay. So the electronics courses, as I stated earlier, that you took so far was 113 to 11 to 12. Oh, sorry, for circuit analysis. Now for electronics, you're taking EE306, where you're learning the fundamentals of semiconductors and semiconductor devices, right? We'll start with P-type semiconductor, N-type semiconductor, bring them together, we form p-n junction. We look at what happens at the p-n junction boundary. Then we add one more junctions to it. We add one more junction to a two-junction and create a two-junction device. So we make a PNP or a NPN junction, and that is what we're going to study in here. Then these are the building blocks for the next classes that you're going to take, 307, 308. 307, you will create digital circuits, digital logic circuits, using the devices and the models that you learn in 306. 308, you learn to develop and analyze analog circuits, okay, analog integrated circuits. Again, using the same models that we use, that we learn about in 306. So in 307, it's digital. Digital, as you all know, has only two values, binary, 0 and 1. So a transistor that we will learn about in this class will be either on or off, okay? And hence digital. So it's called switching circuits. And we use that to build computing devices, okay, computers. And analog circuits basically use the same device, but it's a different region of operation where we can use the amplifying properties of the transistor device. So it amplifies the signals, and we refer to that as the analog portion or analog analysis, okay? So 306 flows directly into 307, 308, and then on the level, you put it all together, EE409, electronic design, which is mixed signal electronics, meaning analog as well as digital. Okay, analog as well as digital. One of the most common examples I like to use, and which I learned from Sid Vyas, another colleague of ours here, is a smartwatch. Smartwatch has sensors, it has computing power. Smartphones for that matter too. And so if you have any kind of smart device, watch, phone, etc., it's an example of a mixed signal electronics device. It has sensors and it has computing. Okay, so sensors plus computing, and referred to as mixed signal electronics. So as I'm always fond of stating, 113 and 306 are two of the most important courses that you would ever take as a EE student. Okay. All right, evolution of electronic devices. How did we get here, right? This is more than a century of work that's been going on for a long time. So early on, the first electronic device was a vacuum tube. Now, when you talk about vacuum tubes, compared to the modern day electronic devices, quite large. Okay. The sizes that you see here, let me see. Let's point out this first one right there, bottom one. Probably the size of a finger. Okay, size of a finger, at least half a finger. So a vacuum tube essentially had two electrodes inside a glass tube held at a vacuum. It's completely sealed at a vacuum. And this electrode was known as the cathode. And this one is known as a anode. There used to be a filament to heat the cathode. And the filament gets really, really hot. The cathode, which is held in close proximity to that filament, also gets hot. Ions float above the cathode surface and just float above the surface without any external bias. When an external voltage or an external energy source was connected between the anode and the cathode, you have the positive end of the energy source connected to the anode. The negatively charged electrons here would be attracted towards the anode. And you have electrons flowing through that tube and through that circuit in one direction. Make sense? Right? If you reversed it, then the negative end would be here, positive would be here, no more current flow. So it was a one-way device. It was a one-way device, could be used for rectification. Okay, current flow was, well, actually, electron flow was in one direction. And this vacuum tube came to be known as a diode. Two electrodes, diode. That's where the name came from. And when they created the solid state version of this device using a semiconductor device, the name carried on. And hence we still use a diode, even though we do not have an actual electrode in the device. Still came to be known as a diode. That's where the name comes from. So you have a vacuum tube element. You have two electrodes inside it. When you heat the filament, you have a lot of free electrons available for conduction, and you apply an external energy source. The electrons are attracted, and you have current flow through that device. Now, a very basic diode like this would have large variations, would not work very well without, you could not control the flow very well just between the anode and the cathode. And so they inserted another electrode on the side, somewhere here, to actually control the flow of the electrons in a better manner. So the third electrode, and that came to be known as a triode. And then they kept inserting more and more electrodes in there, try to obtain better control, more functionality, introduce more functionality in the device. And so from diode, we went to triodes, quatrodes, pentodes, and so on and so forth. If you look at some of these devices right here, it's probably very hard to see. I'm not certain how many these have, but you can see there are multiple devices. You can see a wrap around electrode around it, right? Inside here. And so those could be an example for a triode or a higher number of electrodes inside one vacuum tube. Okay. Anyway, these were the first electronic devices. Okay? First electronic devices, and I'm talking about the early 1900s. Okay, early 1900s. The first actual computer built on this, well, large-scale computer built using these vacuum tubes was known as ENIAC. ENAIC, or is it numerical analysis integrated circuit? And it was installed at UPenn, University of Pennsylvania, on a military grant. It contained, I think, 75 to 100,000 vacuum tubes. Cost about $500,000 at that time. And if any part was non-functioning, it would take more than a day just to locate the faulty vacuum tubes and replace them. Very, very complex. So when you get a chance, you can look it up. From vacuum tubes, we went to discrete devices, discrete transistors, which in the lab 346, you will be working with discrete transistors that look like these. Metal can package and epoxy packaging. You'll have both in your lab kits. From there, we went to integrated circuits. And then, of course, modern day surface mount devices. These, by the way, are simply the packaging. Okay, the actual chip inside it is probably this small. Probably not even that big, far smaller than that. It's incredible how much we can fit onto an integrated circuit by using like modern day fabrication technologies. Which brings me to two more classes. If you wish to learn further about how actual microchips are made or how semiconductor fabrication takes place, you have like one major class you can take in your fourth year. It is EE 423, Introduction to Micro Nano Fabrication. It is actually a biomedical class, BMed 434. And Professor Ben Hawkins teaches this class, the lecture class, and then there's an associated lab section. And Hans Meyer, Ben Hawkins, and me, we each take one section to teach the actual fabrication. Students go inside a clean room. Cal Poly actually has a clean room. How many of you knew about that? Okay, some of you do. The clean room is an environment where engineers and technicians go inside the environment and we create or build microfabricated, well, integrated circuits. We take an actual silicon wafer, students come in the lab, and we build on that every single week. At the end, we create diodes, transistors, solar cells, and some resistors on one single big wafer. And so that class is EE 473. That's the associated lab class. And that is actually my wheelhouse. That is, I spent like several years doing this as a grad student and as a researcher. So this is the lecture. This is the lab. And then also here, our retired professor, Dr. David Braun, started this class, Polymer Electronics. Anyone know which lab this is taught in? You know? No? It's in room 105, right here in this building. It's a very ingenious way of creating a clean room in a small lab facility. So there's a room which has different chambers and boxes inside it. A clean room is an environment, something like this. It's a huge room, completely devoid of small particles, hence the name clean room. And we go inside the environment to build our microchips. The setup in 105, the environment is a small chamber, and we are outside of the small chamber, and we interface with the internal environment using gloves. Okay, and so this is simply a lab course. So again, it ties into semiconductor manufacturing. Okay, coming back here, VLSI surface mount devices. All right. Any questions so far? Yes. Okay, so the question being asked is what was the yield rate of the devices we make in 473? It varies, but it's very low. And that's not a criticism of students or the instructors. That's just the way microfabrication goes. Let me explain in short. Everyone is familiar with PCBs, right? PC, printed circuit board, is nothing but components mounted on a board, and you're running wires from point A to point B, point C to point D, right? That's what a printed circuit board is. A microchip, the simplest explanation I like to use, is basically a miniaturized or micro version of a printed circuit board. You have transistors on your silicon chip, you have diodes, you have lots of other components, and all you're doing is you're running a wire from point A to point B to point C to point D. But it's all at a micro level, meaning so small we can't even visualize it. We can't see it, sorry. And it's hard to visualize it until you've actually seen it under a microscope. Very, very small. So when you're working with such small scale features, even tiny dust particles are the size of huge boulders. Imagine if you're trying to build a road on a pathway and you have a big rock in the middle, big boulder in the middle. Your road's not going to get built, right? So in the same manner, if you're trying to build a microchip, trying to run a wire from point A to point B, trying to create a device, tiny dust particle is the size of a huge boulder, that wire will not work. Hence, you need a room that is very, very clean. To give you an idea of how clean it is, in a room like this, you have about 1 million or 2 million particles in a small cubic centimeter space, about the size of 0.5 microns or small. In a clean room, depending on the classification, it'd be less than 10. Modern day clean rooms, it's less than 1. So it's class 1, class 10, class 100, class 1000. So we have a class 1000 facility here. When I was a grad student, we had a class 100 and a 1000. At UCSB also, they have class 100 and class 1000. So depending on the classification, sometimes, your devices would end up working well just because of, how much contamination occurs in the process. Okay, the modern electronics era began truly in 1947. Okay, that's when the first, that was the one of the first. I want to say one of the first because all research discoveries are always based on something that somebody did in the past. Okay, so there were people who were working on solid state devices like diodes and transistors, but this was the absolute first a demonstration of an actual working transistor. But I always like to use the word one of the first because there were discoveries made earlier than this presentation also. Okay, but by all accounts, this is the one that is recognized the most. Okay, in 1947, there were 3 scientists working at Bell Labs by the name of John Bardeen, Walter Brattain, and William Shockley. These 3 people created a demonstration of a germanium-based single-point contact transistor. And they were able to pass current through this right here and show its rectifying effects. Okay. The 3 of these scientists were awarded a Nobel Prize in physics in the year 1953, I want to say. So it was a groundbreaking discovery at the time. Okay. There are very interesting stories about these 3, especially about Shockley. Okay. From the discovery of the transistor, or not the discovery, I would say the demonstration of a working transistor, we then moved into the era of integrated circuits. Integrated, as the word suggests, you take different components or discrete components and integrate it all onto one single chip. That's what we call as a microchip, right? It's a small chip, integrates large amount of discrete components onto one piece of silicon die or silicon material, hence the name integrated circuits, or IC for short. And in modern day layman terminology, we call it microchips. There was simultaneous development of this integrated circuit. There was a race, as always, in research. In 1958, Jack Kilby at Texas Instruments, and then Noyce and Moore at Fairchild Semiconductor were credited with creating that integrated circuit. Jack Kilby was awarded the Nobel Prize in Physics about 40 years later for the discovery of, well, not discovery, but the invention of this integrated circuit. I think he is a very rare example of somebody who did research work or is credited with a discovery that is not directly associated with physics. At least that's what they say. Anyway, so Jack Kilby at Texas Instruments, he is also credited as being the inventor of the devices that you use, the engineering calculator, Texas Instruments, TI-83, TI-84 Plus. He was one of the first persons, he was the lead person and credited with the invention of the calculator. Since I spoke about the stories, let me speak a little bit about these three people. So all three of them were brilliant. And a lot of brilliant people do not have a lot of patience. They want to get the work done. So by their very nature, they are jerks, to say the least. All successful people that you see, you know, these famous billionaires, they're all jerks. The reason is because they want to get the work done, meaning I wanted this done yesterday. Why is it not done? Right? They are in the pursuit of something larger. Now, everyone has a personal opinion about them, but from all accounts, William Shockley was like a, first grade. And they had a falling out. Okay. So Brattain and Bardeen left AT&T, like Bell Labs, shortly after this discovery. They were not involved in that transistor research after the 1 year or 2 years. Bardeen went to, I want to say, Illinois University. Brattain went to work for, can't remember exactly. And then Shockley started Shockley Semiconductor. Okay, he also left Bell Labs after a while. He was kind of like a paranoid guy, always pushing and always being paranoid about something. And he hired eight doctoral students, or 8 people with PhDs, the first physicists who worked with him at Shockley Semiconductor. And these were the first people who were hired. And as it so happens that they had a falling out, and these 8 people went above his head to the board or the owner of the company or somebody. Anyway, they went over his head, so he was really ticked off. And these 8 people left his employ shortly thereafter. So they left Shockley Semiconductor. Among them were Robert Noyce and Gordon Moore. We have heard of these names. You are sitting in the classroom that is sponsored by the Noyce School of Computing. The Noyce School of Computing was created due to a grant given to us by the widow of Robert Noyce. Okay, Gordon Moore and Robert Noyce, along with Andy Thiel, they are the 3 founders of Intel. So from Shockley Semiconductor, Noyce and Gordon went to Fairchild. From Fairchild, they went on to found Intel. Okay, and Intel, of course, is still in existence today. Shockley Semiconductor was still in existence until, I want to say, 80s or 90s, until just recently. And they changed ownership and they changed the names, but that's how it works in the corporate world. Bardeen, by the way, is one of only 5 people in the world who have won 2 Nobel Prizes. He won one in physics for the invention of the transistor, and then several years later, he won the second one also in physics for a theory postulating superconductivity. So he's one of only 3. Okay, complex circuits. So we're talking microchips. Intel, like Gordon Moore, predicted, well, not predicted, but while they were working, he was astonished at the amount of progress they were making every single year. Year over year, they could see that the number of transistors in a package in a single silicon package was almost doubling. Okay, almost doubling. So he made a prediction that every 24 months, the number of transistors that we are making, that we see in, in the silicon die, will double every 24 months. And that came to be coined and known as a law, which kind of I disagree with. It's not a law, it's kind of like a prediction or a theorem, but it's more famously known as Moore's law. It was not coined by him. He made a prediction that this is something that I see, and we will continue to see this in the near future. And not just the near future, long-term future, that law held up. Every single year, the number of transistors on a chip kept doubling. And then there was so he made this at a conference, and one of the audience members coined the term that this is going to be known as Moore's law. Originally, the story goes that he stated 24 months, but there was some other engineer or some other manager at Intel said that it's not 24, it's doubling at 18 months. And so there was confusion between 18 or 24, but Moore was always adamant that he always stated 24 months. So that's what known as Moore's law. So you can see here, starting from 1970s, prediction going all the way to 2030, but we are reaching the limits. We are reaching the upper limits. We are reaching the limits where we are now talking about individual atoms on a silicon chip. Okay. So we are getting into like quantum computing and stuff, way above my head. But you can see it pretty much held true all these years. It's starting to curve a little bit downwards. Okay. And then on the left, what you see here is feature size. Feature size of a microchip refers to the size of the smallest features, not average, but the smallest features on a microchip. Meaning you could have a wire somewhere, or you could have one component with one lead. If the smallest size of that lead is like 1 micron, you would say this chip has a feature size of 1 micron. Okay, in the XY direction. Not the Z direction, XY direction. So feature size refers to the smallest features that are on a microchip. And you can see the feature sizes have been going down. They're getting more smaller and smaller and smaller. And that is the reason why we can fit more number of transistors every single year in the same space. Okay, the number of transistors keep doubling because the feature size keeps shrinking. Now, as engineers, you are dealing with large variations in numbers. At one end, you have very, very tiny features. At the other end, you have very large numbers. So small numbers to large numbers is a large variation. So we use unit prefixes. And you may be familiar with some of these, but I expect you all to memorize and use this entire table. I'm going to ask this on the final exam. Not really. Even I don't remember this entire table. You would expect to remember at least this one's in the middle, right? Everybody's familiar with milli, micro, nano. Nano is like a layman's tech word nowadays. You attach micro or nano to anything and it just becomes high tech, right? But on the other side, you're familiar with kilo, mega, giga, million, billion, right? To give you an idea of how small we are talking about when we use the words micro, this is how small it is. We can visualize and we can see 1 millimeter, right? 1 millimeter is you take 1 meter, divide it into 1,000 parts, it's 1 millimeter. We have our scales, we have our rulers, we can see it. If you take 1 millimeter and divide it into further 1,000 parts, that is 1 micrometer or 1 micron. So 1 micron, which is 10 raised to minus 6, that's where the word microchip comes from, because it's 10 raised to minus 6, is you divide 1 millimeter into 1,000 parts. And if you take 1 micron and divide it into further 1,000 parts, you get 1 nanometer. That small. Okay. So even to see like a feature size of like 10 microns or 50 microns, you would need a microscope. 1 nanometer, you need like highly specialized SEMs and TEMs. Okay. Anyway, you're familiar with capacitor values and inductor values. Most inductor values are in the millihenries. Capacitor values are in the microfarads or nanofarads or picofarads. The currents through electronic circuits are also on the order of like microamps and milliamps. Hence, we use these unit prefixes. On the other side, we have the multipliers 10 raised to 3, 10 raised to 6, 10 raised to 9. And to give you an idea, I will ask you to guess how much is 1 million seconds? Hours, days, weeks? Okay, one guess is few months. Anyone else? Years? Anyone want to calculate? It's about 11 to 12 days. How much is 1 billion? Few years? You really think? It's 31 years. That's the difference between a millionaire and a billionaire in terms of time, right? They like to throw about, oh, the federal deficit is like 1 trillion. It's like, that's crazy numbers. They just throw this number around as if it's nothing. But if you think in terms of time, it's pretty stark. 1 million seconds is just like few days, and 1 billion is about 31 years. That's a lot. If you had that much money, imagine what you could do. Maybe one of you probably would. If you do, come back and find me. All right, so unit prefixes, again, you'll have the table handy. You don't have to memorize it, but at least somewhere in the middle, the middle of the table is something that you should be familiar with. That was the point. All right, signal types. We are familiar with analog and digital signals. We will look at these signals a little bit in this class, but then going forward, again, as I said, 307, 308, you'll be dealing with those a whole lot more. And also, you've already taken 228, right? That's what continuous time signals. In 328, oh, right now, okay, that's discrete time signals. So analog signals basically are continuous values, meaning at any given point in time, it will have a value. Analog means it can have infinite number of values because it's completely continuous with respect to time. Digital signals, not so much. Digital signals have discrete values. Specifically, if you are talking about logic circuits, digital logic circuits, zeros and ones, only 2 values. If you consider the relationship with respect to time, then at discrete points in time, that signal will have different values. But that quantity is often quantized and it has different levels. Let's see. So there's always a need to go back and forth between analog signal and a digital signal, right? We will live in a world of mixed signal electronics. So there would often be a need to convert an analog signal into digital and a digital signal into analog. And so we use converters. ADC is analog to digital converters, and DAC is digital to analog converters, DACs. That's what we call DACs. And so you can see here, if you have an analog signal and you break it up into a number of pieces, you get what is known as a discrete value digital signal. And this breaking up of pieces is known as sampling. You're sampling the signal at discrete points in time, okay? And the rate of sampling, meaning how many samples you're taking. Obviously, if you take here, you can still make out by connecting the dots, you can still have the same shape as that analog signal, but it would not be able to describe it completely. Okay. So there's always a fine line between how many samples we want to take and the quality of our resulting discrete signal. Okay. Anytime you convert from analog to digital by taking samples, you're going to lose information, right? You're losing information between each sample. So if you need a very high quality signal, you want to take more samples, lower quality signal, less samples. Excuse me. This is also a real life example of this would be streaming versus a physical disk. Okay, streaming takes place over the internet. So there's a defined bandwidth that they have to use, right? If the entire highway is wide open, you can stream like a high bit rate or high quality signal, but it requires a huge amount of bandwidth, right? If you have a physical disk, yeah, space is limited, whether it's a DVD or a Blu-ray. A DVD can hold up to 4.7 GB of data. A Blu-ray can hold up to 50 gigabytes of data. So the available storage space in a disk is inherently much larger than anything streaming can provide. Now, more and more compression techniques are coming into everyday use. The companies are always trying to save bandwidth. Well, that's what they're trying to do because they want to take fewer samples and still provide high quality signals. But that's a real life example of where a bit rate or samples, number of samples, which is technically called bit rate, affects your picture quality. Okay. Let's see, how much time do I have? 8 minutes. We can wrap this up in 8 minutes. All right. So the notations we will use going forward, and I just want to do a brief recap. You have currents, you have voltages, you have single subscript notation, and you have double subscript notation. So reference directions and voltage polarities you're all familiar with. I just want to do a little bit of a brief recap. So if you have two subscripts on a current or a voltage quantity, then it points from the first to the second. An example would be if you're in a lab and you're trying to measure current IAB, meaning current flowing from point A to point B, then you would take the positive lead of your multimeter, connect it to the first subscript, and the negative to the second one. So your point of reference is always the second subscript. The negative end, the common terminal on the multimeter, will always go to the second subscript. Okay. IAB means current flowing from A to B. IBA means current flowing from B to A. And mathematically, of course, IAB would be minus IBA and vice versa. And IBA would be equal to minus IAB. It doesn't matter what you refer to. The plus and minus is just for us humans. We need to balance out equations. If we don't have a plus and a minus sign in our quantities, our equations would never work. They would never balance out. Okay. So that's the double subscript notation for current. For voltage, same thing. VAB means you're measuring the voltage at point A with your reference at B. That's what it means. So if you're in the lab and you're asked to measure VAB, the positive terminal of the meter should always be at A, the negative should always be at B. And that's what it means. Voltage, of course, is the difference in potential between any 2 points. If both points are at the exact same potential, the voltage between those 2 points is 0. One of those points has to be higher than the other for there to be a potential difference. So same manner, VAB is minus VBA, and VBA is minus VAB. Okay, that's the two subscript notation. Now, let's take a pause. 10-second pause. Let me know if you have any questions. Any questions? So in electronics, we'll be working with both AC as well as DC, right? AC as well as DC signals. So the total voltage or total current appearing at any given point in the circuit is comprised of both AC as well as DC voltages. So to differentiate between the two, and maybe you're familiar with this, maybe you're not, but this is what we'll use. You have a lowercase quantity, V and I, right? V and I. So it's lowercase. Or we used to say small and capital. Small letters and capital letters. With uppercase subscript. That refers to the total quantity, total signal at any given point in the circuit. Okay. Lowercase quantity with uppercase subscript. VT and IT. And then DC is all uppercase and AC is all lowercase. Okay. Or all capital letters, and AC is all lowercase. So you have to keep this in mind when you're looking at any circuit or any problem. To give you an example, we will look at something known as VBE. VBE. Voltage as measured from the base to the emitter in a transistor. It's one of the most common quantities that you look at. So you have a lowercase, in case this is not clear, I'm going to write it like this. It's lowercase quantity with uppercase subscript. So it's talking about, or it's referring to the total signal between base and emitter. Right? The total voltage available at the base when measured with respect to the emitter. And then VBE would comprise of the DC voltage or DC biasing voltage plus the AC applied signal, all lowercase. Okay. All lowercase. So DC voltage plus the AC voltage. Make sense? Right? So keep that in mind as we go along in this course. Also, as an electrical engineer, this is the standard that is used worldwide. There are a couple more slides, but we'll leave them for next class. So we'll end class here today. If you have any questions, I have 10 minutes before next class begins. Otherwise, I'll see you all on Friday. Yes. Yeah. Yep. So was it quiz one or homework one? Homework one. Yeah. On Connect. Yeah.
That's the scan one, right? The scan will be bigger.
All right. Let me look it up.